Electric fields, part 1, uniform fields. Now, what is an electric field? An electric field is a region of space where charges experience forces. There's an electric field in this region of space, there's a charge, it's experiencing a force. Now, the strength of the field is defined as the force per unit charge. So big E is F over Q, and big E is measured in newtons per coulomb, the force per unit charge. The direction of the field is the direction of the force on a positive charge. If there was a negative charge on this diagram, then the force would be in the opposite direction. As it's a positive charge, then the force is in the direction of the field. A uniform field. In a uniform field, the field strength is the same everywhere. So between two parallel metal plates, this produces a uniform field, and we can represent the field by drawing field lines. And our field lines in a uniform field are parallel and straight and evenly spaced. A very common exam question is to just sketch the field lines between parallel plates. Note that the arrows go from positive to negative because that is the direction of the field. Now, if we put a positive charge at Q and let go of it, it would move towards the negative plate. It would experience a force F equals EQ, and it would accelerate towards B. If we had a positive charge at B and we wanted to move it to A, then we would have to do work. Work equals force times distance to move it from B to A. Now, in both cases, the energy transferred, we have energy transferred equals force times distance, and we have energy transferred equals QV. A very important equation that you should remember from year 1. So, looking at that and rearranging it, that tells us that in a uniform field, big E, which is F over Q by definition, is also equal to V over D. But that's just for a uniform field, E equals V over D. Also, therefore, electric field strength can be measured in newtons per coulomb or volts per meter. Here's a sum for you to do. Two parallel metal plates, 5 centimeters apart, have a PD of 200 volts across them. Calculate the field strength and what force would act on that charge. I'll give you a second. And the answer is that. Hopefully you agree. Here's another slightly trickier one. It brings in some forces and things. A very common type of question though. A light charged ball of mass that, suspended by an insulating thread, is placed in a field as shown. The plates are 15 centimeters apart, have 200 volts across them. The thread is dangling at 15 degrees to the vertical. First of all, draw a diagram of the ball showing the forces acting on it. Calculate the size of each force. Have a go at that yourself, and the answer is that. So I've resolved vertically to find the tension, and then I've used that resolved horizontally to find the charge. Of course, if you're good at maths, you might have realized that t sine 15 divided by t cos 15 is tan 15, and the t's cancel, and you could have done it in one step. Electrical potential. Now, the potential at a point is the electrical potential energy that unit charge would have at that point. With my students, I introduce them to my little friend Colin the Coulomb, and I say the potential at a point is how much energy Colin the Coulomb would have at that point. Now, looking in this diagram of a uniform field, we can see how the potential varies in between. In a uniform field like this, we take the zero of potential to be the negative terminal of the power supply. We assume that that is earthed. Equipotentials in a uniform field, they are evenly spaced, parallel and straight. Of course, they're not lines, they're actually 2D surfaces. They're always at right angles to the field lines. The potential gradient is constant. Because the potentials are evenly spaced, if you did a graph of potential against distance, it would be a straight line. The potential gradient is constant, i.e. V over d, which is the field strength. The potential gradient is the field strength. And then the energy transferred moving a charge from one point to another is QV, as we said earlier. Okay, useful to think of them as like levels in a car park, perhaps. Here's a question you can have a go at, pretty straightforward. I'll let you read it, pause the video, have a go at it. And that is the answer you should get. Finally, when we're on uniform electric fields, you should know about Millikan's oil drop experiment. Robert Millikan, very clever bloke, did an experiment, spent many years making the experiment better and better to find the charge on an electron. Basically tiny little oil droplets in an electric field, and they are suspended by the field. Now, a very simple way of thinking about it is imagine a drop in equilibrium. So there is its weight pulling down, there's an electric force pulling upwards. If it's in equilibrium, the forces are equal and opposite. And from this equation, you can work out the charge on the drop. To find the mass of the drop, we know its volume, because what you do is you measure its terminal velocity. From that you can get its radius, you can get its volume. If you know the density of the oil, you can work out the mass of the drop. And so Millikan did this experiment hundreds of times, and what he found was he got lots of values of Q. The smallest value of Q was equivalent to little e, and the rest were all multiples of little e. So Robert Millikan got a value for little e.